Hello everyone, welcome to the world of materials. Materials play very important roles in our daily life. For example, the textbook which is made of, the container we drink with, the quarters, or even the batteries. However, as we all know that everything is made from atoms. So how are those atoms stacking together for these metals? The very basic unit is called the unit cell, and here we have two examples. The left one is called body center cubic, which actually have one atom in the body center, while the other one is called the face center cubic, which has six atoms in the center of each faces. For example, iron and chromium, they are body center cubic, while aluminum, copper, silver, and gold are face center cubic.
So here gives an example for the face center cubic. For example, the atoms here in green stands for the atoms on the corners, while the atoms in red here stands for the atoms in the face centers. For example, this one is for the front face, this one is for the back face. These two are for the sides, this one is for the top, and this one for the bottom. But it should also be noted that those atoms, the real size for those atoms are really small. It's within the nanometer size, which is 10 to the minus 9 meters. So within this kind of cubic, duplicated in all directions, you will finally form the metal that you can see in the real world.
Another interesting topic is called solid oxide fuel cell. Nowadays, the global warming and people's increasing demands for energy have brought up the idea of solid oxide fuel cell because SFC has many advantages over the traditional ways of generating electricity. For example, SFC is much more cleaner as it will emit less carbon dioxide. The choice of the fuel for SFC is much more flexible, and moreover, the efficiency and reliability of SFC is much better than the traditional ways. But how did the SFC really work? And here is a schematic example for the solid oxide fuel cell. You can see that with the fuel supplied to the anode side and the air supplied to the cathode side, the fuel will be oxidized and the electricity can be generated. That is how it works, and thanks for watching.
Good morning, everyone. In this slide, I'm going to introduce the high-entropy alloys. So previously, we have introduced the concept of BCC and FCC structure. It should be mentioned that high-entropy alloys typically have BCC and FCC structure. However, unlike the pure element, which have only one component, a high-entropy alloy typically have more than 5 components, which means each side was occupied by different type of atoms. So because of the atomic size differences, high-entropy alloy will have severe lattice distortion, and it can bring up outstanding mechanical property. So that's why people have strong interest about high-entropy alloys. So one challenge for the investigation of high-entropy alloys is the cost. So typically high-entropy alloy have more than 5 components, which means there are tons of compositions needs to be investigated. So that's why it is impossible to follow the trial and error approach to doing the experiment. However, with the computational approach, we can quickly investigate all of these compositions based on this high throughput calculation. So here is the melting point of BCC and FCC phase. So the red dot is the lowest temperature and the blue dot is the highest temperature. So with this high throughput calculation, we can quickly capture thousands of compositions and the information of FCC and BCC phase. So then this slide, I'm going to introduce 4 types of material showing conductivity physics property. So the first one is the Vento black, the second one is the line X spray, and third one is the Newtonian fluid, and the fourth one is hydrophobic spray. And here is the video, and also you can download or check the video on this YouTube website, and thank you.
I'm going to talk about machine learning for materials. Machine learning is the application of algorithms that provide systems the ability to automatically learn and improve from experience. With machine learning, a computer can learn to do tasks on itself. So, how is machine learning used in material science? Let's take the example of metallic glass. Metallic glass are amorphous alloys that are glass-like. They form when metals are mixed at certain ratio. The points in the triangle diagram shows you at what ratios metallic glass are formed. Now we want to know more mixtures. So we tell the computer which mixtures are glass and ask it about mixtures we do not know. The computer processes the given information and gives predictions on things we don't know. In this case, instead of the points we have in the beginning, machine learning tells us a lot more mixtures where metallic glass are formed.
Molecular dynamics is a computer simulation method for analyzing the physical movements of atoms and molecules. We all know this world is built by different atoms that contain nucleus and electrons, and a large number of different kinds of atoms will come together to form molecules or crystalline structure. In the scale that we can see through our eyes, this is so-called materials. But how do these atoms or molecules affect our materials and exhibit different properties? For example, in alloys, if you cut a sample and look at the surface under a microscope, you will find many polygonal areas called grains. When we process an alloy by heat treatment in order to increase its strength or ductility, the size of grains will be changed. In fact, most of mechanical properties of alloys are controlled by their grain size. Through the molecular dynamics, we can simulate the process and rate of grain growth and calculate the average size of grains under certain experimental conditions, then estimate the properties of this material. The principles of molecular dynamics is very simple. It is a motion of Newton's equation that we learned in high school. Force equals mass times acceleration. This is for only one item. There is no problem to figure it out by our hands. But how about two items, 10 items, or even more? This will be a little complicated. Fortunately, we have supercomputer now. All calculations can be done by computers. For example, this is a simulation of movement of a nanoparticle in cold spray process, and this is a molecular motor and the DNA animation in your body cells, and on the top right are the water molecules.